Okay, welcome to today's tutorial. In this video, we're going to look at overtone and the relationship between harmonic frequency and overtone, right? So, what is an overtone? An overtone is any natural frequency of vibration of a body higher than its fundamental frequency. So, any natural frequency of vibration of a body that is higher than the fundamental frequency, that frequency is referred to as what? An overtone. So, what is then a fundamental frequency? Fundamental frequency is the lowest natural frequency produced by a vibrating body. The lowest natural frequency produced by a vibrating body. So, any frequency that is higher than this lowest natural frequency, which is referred to as the fundamental frequency, that frequency is referred to as what? An overtone. So again, an overtone is any natural frequency of vibration of a body higher than its fundamental frequency. Then harmonic frequencies. Harmonic frequencies are the whole number multiples of the fundamental frequency, right? So harmonic frequencies, they are the whole number multiple of the fundamental frequency, right? So it's very important that we know the relationship between overtone, harmonic, and what? Frequency. So harmonic frequencies are whole number multiples of the fundamental frequencies, right? So the fundamental frequency is written as F1. This is the lowest natural frequency produced by a vibrating body, right? And it is the fundamental frequency. It is fundamental because it is the lowest natural frequency, right? So it is F1. So the first harmonic frequency is equal to your fundamental frequency. And what that means is that there is no overtone. What is an overtone? An overtone is any frequency that is higher than the what? The fundamental frequency, right? So the first harmonic and harmonic frequencies, like I said, they are whole number multiple of what? Of the fundamental frequency. So if the fundamental frequency is F1, times 1 will give us what? F1. F1 times 1 will still give us F1, right? So that's the first harmonic. They are whole number multiple of what? The fundamental frequency. So the first harmonic is what? F1. And there is no overtone in the first harmonic. The second harmonic will be the fundamental frequency times what? 2. That will be equal to what? 2F1. That's 2 times the fundamental frequency. That's the second harmonic. Remember that they are whole number multiples of what? The fundamental frequency. So 2 times the fundamental frequency will give you the second harmonic. And that is equal to your first overtone, right? An overtone, like I said, is the natural frequency of a body that is higher than the fundamental frequency. So it's higher than the fundamental frequency by what? 2. It's very important that you should know that your first overtone is equal to your second harmonic. Then the third harmonic is equal to what? Your second overtone. Your fourth harmonic is equal to your third overtone. So know this relationship, right? First harmonic means there is no overtone. Second harmonic is equal to your first overtone. Third harmonic is equal to your second overtone. And your fourth harmonic is equal to your third overtone, right? So let's look at the overtone in vibrating strings. So in a vibrating string, let's say this is a string, right? When both ends are fixed, both ends are fixed. So in a vibrating string where both ends are fixed, the fundamental frequency F1 is equal to V, which is the velocity, over 2L, where L represents the length of the string. So your L here is the length of the string, V is the speed of wave on the string, which is the velocity on the string, then F1 is the fundamental frequency, and the fundamental frequency is referred to as the first harmonic. And in the first harmonic, there is no overtone, right? So this formula is very important for getting the first harmonic. or the fundamental frequency. F1 is equal to V over 2L. So the second harmonic will now be F1 times 2, right? F1 times 2. So the second harmonic is 2 times what? F1. And so if our F1 is given as V over 2L, that means that my F1, instead of me to, if my F1 is written as V over 2L, that means this will now be 2 times what? V over what? 2L. Why? Because my F1 is V over 2L, right? As given here. So 2 times V will give me 2V over what? 2L. 2 will cancel out 2 to remain what? VL, right? So my F2, which is the second harmonic or the first overtone, is equal to V over L. And that is what we have here, V over L, right? This is the F2, and it is equal to the first overtone or the second harmonic, right? Then the third harmonic or the second overtone, it will be 3 times the first harmonic, right? 3 times the fundamental frequency. So 3 times this, so that would be 3 times the fundamental frequency, which is V over what? 2L. So 3 times this will give me 3V over what? 2L. And that is what we have here as the third harmonic or the second overtone, right? So the fourth harmonic, F4, will be equal to 4 times the fundamental frequency, which is V over 2L, right? So 4 times V will give me 4V over what? 2L. 2 here is 2, 2 here is 1. So that will be equal to 2V over L. This is our what? Fourth harmonic or the third overtone, right? Remember what I said before, that the first harmonic means there is no overtone, and that is equal to the fundamental frequency. Your second harmonic is equal to your first overtone, third harmonic is equal to your second overtone, fourth harmonic is equal to your third overtone, right? So that's that for overtone in vibrating strings. So let's look at overtone in open pipes when both ends are open. So this is also equal to your overtone in vibrating strings. This is an example of a pipe where both ends are open. The same formula that we use for calculating overtone in vibrating strings, that is the same formula that we use here in open pipes where both ends are open, right? So the fundamental frequency is equal to V over 2L. Second harmonic is equal to V over L, and the third harmonic is equal to 3V over what? 2L. The fourth harmonic, F4, will be equal to 4 times the fundamental frequency, which is what? V over 2L. So that will be equal to 4V over 2L. 2 here is 1, 2 here is 2. So that will be equal to what? 2V over what? L. So if we're looking for the fifth harmonic, which will be equivalent to the fourth overtone, that will be equal to 5 times the fundamental frequency, which is what? V over what? 2L. So this will be equal to 5V over what? 2L. This is our fifth harmonic or the fourth overtone, right? So the same formula that we use in calculating the overtone in vibrating strings, that is also the formula that we use in calculating the overtone in open pipes where both ends are open, right? So let's look at examples. The first example that I have here is a rope with length 2 meters is stretched between two supports with a tension that makes the speed of transverse waves 40 meters per second. Full stop. Find the length and frequency of A, the zero overtone, B, the first overtone, and C, the third, right? So let's put our solution here. The first thing I will want to do is to fish out the parameters that are given in this question. So the question again says a rope with length 2 meters. So the length of the rope is what? 2 meters. Is stretched between two supports with a tension that makes the speed of transverse waves 40 meters per second. So the speed of the transverse wave is what? 40 meters per second. Find the wavelength and frequency of A, the zero overtone, B, the first overtone, C, the third harmonic. So the first thing that we're going to look for is the wavelength and frequency of the zero overtone. So the zero overtone is equivalent to what? Your first harmonic. The zero overtone is also equivalent to what? Your fundamental frequency. So if we go back to that table, the first harmonic is your fundamental frequency, and there is no overtone. The second harmonic is 2 times your fundamental frequency, and that is your first overtone. Third harmonic is your second overtone. Fourth harmonic is your third overtone, right? So the zero overtone is what? Your fundamental frequency. Is your fundamental frequency, and it is your first harmonic, right? So we're looking for the wavelength and frequency of the zero overtone. So the wavelength of, how do we calculate the wavelength of the zero overtone? So you should know that your wavelength of the zero overtone is represented as what? Lambda 1, to tell you that it is fundamental, right? It is fundamental, is equal to 2L over what? Over the number of harmonic, which is what? 1. Because it is 1 here, it will be 1 here, right? This is the formula that you use, right? So the wavelength of this zero overtone or first harmonic 1, lambda 1 is equal to what? 2 times what? L. What is your L? Your L is 2. So that will be 2 times 2 divided by 1. And that will be equal to what? That will be equal to 4, right? So 4 divided by 1 is still 4, right? So that will be 4 meters. This is your wavelength for the zero overtone. Then the next thing I would want to look for is to look for the frequency, because the question says find the wavelength and frequency of what? The zero overtone. So we'll look for the frequency of the zero overtone. So the frequency of the zero overtone, which is the fundamental frequency, is equal to what? It is equal to V over what? 2L, right? So frequency, the fundamental frequency or the zero overtone is equal to, the frequency of the zero overtone is equal to, our V is what? 40. So that will be 40 divided by what? 2L, right? 2 times what? Our L is what? Is 2. So F1 will be equal to what? 40 divided by what? 40 divided by 2 times 2 is 4, right? So 40 divided by 4 is equal to what? Is equal to 10. So my fundamental frequency is equal to what? 10 Hz, right? This is the frequency of the zero overtone, or the fundamental frequency, or the first harmonic, right? Then B, we're looking for, B says find the length and frequency of the first overtone. So the first overtone is equivalent to your second harmonic, right? It's equivalent to your second harmonic. So the wavelength of the second harmonic, which I will represent as lambda 2, will be equal to 2L divided by what? Divided by 2. I will not write 1 here. I will divide it by what? The number of harmonic, which is what? 2, right? So that will be lambda 2 is equal to 2L, 2 times our L is what? 2, divided by what? 2. 2 cancel out 2, right? So the wavelength of the second harmonic, which is this first overtone, is equal to what? 2 meters. This is your answer, right? Very simple and straightforward. Then the next thing is to look for the frequency of what? The first overtone, which is your second harmonic. So F2 will be equal to what? Your F2 will be equal to 2 times what? Your F1. Remember that harmonic frequencies, they are whole number multiples of what? The fundamental frequency. So my F2 which is the frequency of the first overtone or the second harmonic, is equal to 2 times the fundamental frequency is what? Is 10. So that will be equal to 2 times 10 is what? 20 Hz. This is the frequency of the first overtone, which is equivalent to what? Your second harmonic. Then the next question, the last question here, is to look for the wavelength and frequency of the third harmonic, right? So the wavelength of the third harmonic, this is your question C now. The wavelength of the third harmonic, which I will represent as lambda 3, will be equal to 2L divided by what? 3, which is the number of harmonic, right? So my lambda 3 will be equal to 2 times, the value of L is what? The length is what? 2 divided by what? 3, right? So lambda 3 will be equal to 4. 2 times 2 is 4, right? 4 divided by 3. So 4 divided by 3, that will be equal to what? 4 divided by 3, that is equal to 1.33, right? So that will be 1.33 what? Meters. This is the wavelength of the third harmonic, which is equal to what? The wavelength of the second overtone. Then the next thing is to look for the frequency, right? So the frequency of the third harmonic, which is F3, will be equal to 3 times what? F1. So that will be equal to 3 times the fundamental frequency, which is what? 10. So 3 times 10 is equal to what? 30 Hz. So this is the frequency of the third harmonic, 30 Hz, right? So this is your F3. This is your F2, right? So this is a very simple and straightforward concept. Let's look at the next question that we have here. And the question is to calculate the frequency of the first overtone of a stretched string of length 60 centimeters if the velocity of sound produced is 330 meters per second, right? So let's put our solution here. The first thing I would want to do is to fish out the parameters. The question is calculate the frequency of the first overtone. Calculate the frequency of the first overtone. So your first overtone is equal to what? Your second harmonic. So what we are looking for is what? F2. That was what we are looking for. Calculate the frequency of the first overtone of a stretched string of length 60 centimeters. So the length is what? Of the string is 60 centimeters. And centimeter is not the fundamental unit for length, right? The fundamental unit for length is what? Meters. So I will have to convert this 60 centimeters to meters. 100 centimeters is equal to what? 1 meter. So therefore 60 centimeters will be equal to 60 divided by 100, right? So 60 divided by 100 will give me 0.6 meters. So my 60 centimeters is equal to 0.6 meters. So calculate the frequency of the first overtone, which is the second harmonic, of a stretched string of length 60 centimeters if the velocity of sound produced is 330 meters per second. So the velocity of the sound is what? 330 meters per second. We are asked to look for what? The second overtone. So the first thing I would want to do is to write out the formula. So we know that the fundamental frequency of a stretched string of a vibrating string is equal to what? Is equal to V over what? 2L, right? So since what we're looking for is the second harmonic, so my F2 will be equal to what? 2 times what? V over 2L, which is 2 times what? F1. 2 times F1. My F1 is what? V over 2L, right? So that will be 2 times my F1, which is V over 2L. So this will now be equal to 2V over what? 2L. 2 we cancel out 2, right? So my second harmonic, which is F2, is equal to V over L. So F2, which is the frequency of the second harmonic, is equal to V over what? L. So my V is what? My V is 330 divided by L is what? 0.6. 0.6. So 330 divided by 0.6, that will give us 330 divided by 0.6, that will give us 550, right? So the frequency of the second harmonic is equal to what? 550 hertz, right? This is the frequency of the second harmonic or the first what? Overtone, right? So let's look at the last question that we have here. And the question is, find the first four harmonic for a string that is 2 meters and the linear mass density of 2.5 times 10 raised to the power minus 2 kg per meter and is under tension of 40 Newton, right? So the first thing I would want to do is to fish out the parameters that are given to us in this question. So the question is, find the first four harmonic for a string that is 2 meters. So we are looking for F1, we are looking for F2, we are looking for F3, and we are looking for F4, right? That is what we're looking for here. Find the first four harmonic for a string that is 2 meters. So the length of the string is what? 2 meters. And linear mass density of 2.5 times 10 raised to the power minus 2 kg per meter. So the linear mass density is equal to what? 2.5 times 10 raised to the power minus 2 kg per meter. And this is equivalent to 0.0, showing us the number of 0, that's the minus 2 here, 0.025, which is this 25 that is here, right? Kg per meter. Then, and is under tension of 40 Newton. So the tension is what? 40 Newton, right? So how do we go about calculating this? So the first harmonic, which is your fundamental frequency for a vibrating string, is equal to what? Is equal to V over what? 2L. This is the formula for calculating the fundamental frequency of a vibrating string, right? F1 is equal to V over 2L. So we were not given velocity here, but we can look for the velocity, right? So the velocity of a transverse wave, or the velocity of a wave on a string, the velocity of a wave on a string, V, is equal to what? The square root of T over what? Over U, over the linear mass density, right? So we are given that the tension on the string is what? 40. So this will be equal to the square root of 40 over 0.025, which is the linear mass density, right? 0.025. So 40 divided by 0.025, what would that give us? 40 divided by 0.025, that will give us 1,600. So this will be equal to the square root of 1,600, right? The square root of 1,600. So the square root of 1,600 is what? Square root of 1,600, that is equal to what? 40. So the velocity is equal to what? 40 what? 40 meters per what? Seconds. So our velocity is equal to what? 40 meters per second divided by 2 times what? Our L is what? 2 meters. 2 meters from the equation. 2 meters. So times 2. So this will be equal to 40 divided by what? 2 times 2 is what? 4. That will be equal to 40 divided by 4 will give me 10 hertz, right? So this is my fundamental frequency. So my second harmonic, so this is equal to 10 what? Hertz. So my second harmonic, F2, will be equal to what? 2 times what? My F1. So that will be equal to 2 times what? My F1 is 10, right? So that will be equal to 2 times 10 is equal to what? 20 hertz. So my second harmonic is equal to what? 20 Hz. Then my third harmonic, which I will represent as F3, will be equal to 3 times my fundamental frequency, right? So that is equal to 3 times what? Times 10. And 3 times 10 will give me what? 30 Hz. So my third harmonic is equal to what? 30 Hz. Then my fourth harmonic, F4, will be equal to what? 4 times the fundamental frequency, F1, which is what? 10. And that is equal to what? 40 Hz. So my fourth harmonic is what? 40 Hz, right? So the first harmonic, there is no overtone. Second harmonic is the first overtone. Third harmonic is the second overtone. Fourth harmonic is the third overtone, right? So this is a very simple and straightforward question, right? So just a quick recap. We discussed what an overtone is, and I said overtone is any natural frequency of vibration of a body higher than its fundamental frequency. And the fundamental frequency is the lowest natural frequency produced by a vibrating body. Harmonic frequencies, they are the whole number multiples of the fundamental frequency. So like I mentioned before, your first harmonic is equal to your fundamental frequency, right? And there is no overtone. Your second harmonic is 2 times the fundamental frequency and it is equal to what? Your first overtone. Third harmonic is 3 times the fundamental frequency and it is equal to your second overtone. Fourth harmonic is your third overtone, right? And we looked at the overtone in vibrating strings, and the fundamental frequency is what? V over 2L. This formula, very important, and it applies to the overtone in open pipes where both ends are open. So you can see that both ends are open. So your fundamental frequency is equal to what? V over what? 2L. Then for a closed pipe where both ends are closed, your fundamental frequency is equal to V over 4L. So in the next video, we're going to focus on questions and explain the overtone in closed pipes better. Thank you very much for listening. See you in our next video.